Let us continue chemical properties of ether. Now we will write diethyl ether. We will take diethyl ether. It is reacting with the PCl5, phosphorus pentachloride. So what is the product? We will see. Here this bond is breaking, here one Cl, this bond is breaking, here Cl, remaining is PCl3, that we will write. Okay, this we can write C2H5Cl, we can write. This is also C2H5Cl. This is what in the sense POCl3. POCl3, phosphorus oxide trichloride, we can say. Next, ether we are taking to this, it is exposed to air, atmospheric air, and light is exposed to this, and it is left for long time. This ether undergoes oxidation with atmospheric oxygen, to give what in the sense hydroperoxide, otherwise peroxide. Okay, so we have taken ether. This ether is exposed to atmospheric air, and light is it is exposed to light, and it is left in so and so for long time. It is undergoing oxidation to give what in the sense hydroperoxide or peroxide. Okay, so ether example we will take, that is diethyl ether. We will take diethyl ether with oxygen. In the presence of sunlight, it is undergoing oxidation to give hydroperoxide. How the hydroperoxide is formed in the sense so and so. So and so hydroperoxide is formed. So and so hydroperoxide is formed. What is the name of this one? That we will see. Now, this part we will call it as ethoxy. Then this part we will call it as ethyl. This part, remaining part is called hydroperoxide. This is ethoxy, this is ethyl hydroperoxide. Ethoxy, ethyl hydroperoxide. Hydroperoxide present at which carbon? At first carbon. Therefore, we can say like this. Otherwise, ethoxy present at first carbon. So, 1 ethoxy ethyl hydroperoxide. Like this, we can write. So, what is the mechanism involved here in the sense free radical mechanism? Free radical mechanism is involved here. Light is there means free radical mechanism. Then here oxidation takes place at which carbon? We'll see. In this one, oxidation takes place at which carbon means the oxidation takes place which carbon means the carbon which is directly attached to ethereal oxygen. At that carbon, oxidation takes place. The which carbon is directly attached to ethereal oxygen, to that carbon will undergo oxidation. So, then how to deduct this peroxide? So why to deduct this peroxide? If a peroxide is there, it decomposes violently at high temperature. This peroxide decomposes violently at high temperature. Let it decompose. Why we should consider this? In the sense, we are using ether for many cases. In many cases, ether is used as a solvent in the many organic compounds. In the many organic reactions, ether is used as a solvent. For example, Grignard reaction. In the Grignard reaction, ether is the solvent. In the many cases, in the many chemical reactions, ether is a solvent, and in many separations, in many separation of mixture, ether is used as a solvent, ether is used as a separating liquid. Therefore, we are using ether in many cases. But what is the drawback? This ether with atmospheric oxygen and light becomes hydroperoxide. This hydroperoxide decomposes at high temperature. This hydroperoxide decomposes at high temperature means we are using ether in the sense that ether should have hydroperoxide or should not have hydroperoxide. What we have to say? Should not have hydroperoxide. So what ether we are using, that ether should not have hydroperoxide or peroxide. That means before using this ether, we should ensure that hydroperoxide is not there or peroxide is not there. Then only we have to use the ether as a solvent. So first we have to, before using the ether, first we have to see whether this ether contains any peroxide or not. If it is there, that we have to remove, then only we have to use the ether. So how to deduct this hydroperoxide? How to deduct hydroperoxide we'll see. Then how to remove hydroperoxide we'll see. Okay, now we will take the ether. We are taking the ether. This contains peroxide. This ether contains peroxide. That solution we will take. To this, we will add freshly prepared ferrous sulfate solution. Freshly prepared ferrous sulfate solution we are adding. Then we are shaking the contents very well. We are shaking the contents very well. Okay. So then what is added means potassium thiocyanate is added. Potassium thiocyanate is added. What is obtained means red color is obtained. Red color is obtained. This red color is what means FeCNS thrice. Red color is obtained. Sir, how this reaction takes place? That we will see. How this reaction takes place? That we will see. Here, this ether contains peroxide. Okay. This ether contains peroxide becomes ether while this ferrous is converting into ferric. This ferric takes CNS minus and becomes FeCNS thrice. So, that means it is undergoing oxidation here. Here what happens means a reduction is possible. How reduction is possible, that we will see. Here see, this is hydroperoxide. This hydroperoxide contains -1 oxidation number. It is undergoing reduction means it is converting into -2, that becomes water. This oxygen also converting into -2 and becomes water. Then when these two are removed, what is remaining? Ether is remaining. Therefore, this ether containing peroxide undergoes a reduction and becomes ether, while ferrous undergoes oxidation and becomes ferric. This ferric takes CNS minus and becomes ferric thiocyanate, that is a red color. Okay, so this ferrous is undergoing oxidation because peroxide undergoing reduction. Okay, so if you get red color, that indicates peroxide is present. Now, this ether containing peroxide is colorless. Ferrous sulfate solution is pale green. Potassium thiocyanate crystals, this solution is colorless. This is red color. Okay, so if red color is formed, that indicates ferric thiocyanate is formed. That means ferrous is converting into ferric. That means here peroxide is present. If peroxide is present, then only ferrous will convert into ferric, otherwise no. Therefore, from this reaction, we can say this ether contains peroxide. Otherwise, this ether contains hydroperoxide. That conclusion we can get it. So, we have deducted the peroxide presence in the ether. So, next, after deducting the presence of peroxide, how to remove this peroxide? That we have to see. How to remove this peroxide? That point we have to see. Okay. So, how to remove peroxide? That point we will see. Now, ether containing peroxide we will take. Ether containing peroxide we are taking. Now to this what we are adding in the sense potassium iodide solution. Then the contents will be shaken very well. Shaken very well. Now what happens means I2 is liberated. I2 is liberated and ether is produced. That means this peroxide undergoing reduction and becoming water. This I minus is undergoing oxidation and become iodine. This I minus undergoing oxidation and becomes I2. This peroxide undergoes a reduction and becomes water. This ether is separate. Okay, so ether containing peroxide. How to remove this peroxide in the sense by shaking with potassium iodide solution. So, next step. This ether containing peroxide is shaken with a freshly prepared ferrous solution. Freshly prepared ferrous solution. What happens means this ferrous is converting into ferric solution and ether containing peroxide becomes ether. This peroxide undergoes reduction and becomes water. Ether is separated. Ferrous is converting into ferric. Ferric goes to aqueous solution. Sorry, how to separate them? How to separate in the sense ether and aqueous solution of ferric do not mix with each other. They will form separate layers. Therefore, separate layers in the sense we can separate easily. So we got ether. So in this method, we can convert peroxide into ether. Ether peroxide we are converting into ether. This ether we can use for whatever the case required. So ether in the sense we should be careful that whether ether contains peroxide or hydroperoxide, we should know it. So we have to deduct it. If hydroperoxide or peroxide is there in the ether, means first you have to remove that hydroperoxide or peroxide. Then only we have to start using ether. Okay, sir. Why? Because this hydroperoxide or peroxide of ether undergoes a decomposition violently at high temperature. For that case only. Okay, sir. Next equation. Next we will see. We'll go for chlorination. We go for chlorination. Now we will take diethyl ether. We will take diethyl ether. We will treat this with chlorine. We will treat this with chlorine in dark. We will treat this with chlorine in dark. What happens means alpha carbon undergoes chlorination. Alpha carbon undergoes chlorination. Alpha carbon undergoes chlorination. Okay, we can call this is as this is alpha carbon containing chlorine. It is alpha carbon containing chlorine. It is alpha carbon. It is alpha dash carbon. So we can say alpha dash dichloro diethyl ether is the name of this compound. Okay, but in the presence of sunlight, how the reaction takes place? The reaction how it is taking place means like this taking place. Okay, this is called what in the sense perchlorodiethyl ether. Perchlorodiethyl ether. Perchlorodiethyl ether means all the hydrogens are replaced by chlorine. All the hydrogens are replaced by chlorine. Therefore, it is called perchlorodiethyl ether. We can say. Okay, so this is called chlorination. In dark, only one alpha hydrogen is replaced by chlorine, but in sunlight, all the hydrogens are replaced by chlorine. We can say. Sir, next we will see aromatic ethers we will take. That means aryl ethers we will take. For that, how the electrophilic substitution reaction is there, that we will see. Now we will take anisole. We are taking a anisole. We have taken anisole. It is going for electrophilic substitution reaction. Now it is this group, this substituent is activating the phenyl ring or deactivating the phenyl ring, whether it is orthopara director or meta director, that we will see. This oxygen is having two lone pairs, therefore it is contributing lone pair, so it is plus R effect. It shows plus R effect. Therefore, this oxygen is activating the phenyl ring towards electrophilic substitution. And since it is showing plus R effect, this is directing the electrophile to attack ortho and para positions, but not on meta position. Therefore, it is ortho para director. So it is activating the phenyl ring, and it is ortho para director. Sir, when shall we say ortho para director and activator? When shall we say meta director and deactivator? When shall we say deactivator and but ortho para director? That we will see. Okay. If in the phenyl ring, the group here, the atom which is directly attached to phenyl ring is having lone pair. Okay, if the atom directly attached to phenyl ring is having lone pair, then we can say that that group act as plus or effect. That group will show plus or effect. Okay, suppose OH. Now see, lone pair is there. So this oxygen atom is directly attached to phenyl ring. It is having lone pair. Therefore, it will show plus or effect. Plus or effect in the sense it will activate the phenyl ring towards electrophilic substitution, and it will act as ortho para director. It will direct electrophile to attack at ortho and para position. Sir. So we will take now. We will take like this. We will take. Okay. Now this atom is directly attached to phenyl ring. It is not having lone pair. Okay, not having lone pair, not having lone pair in the sense not having lone pair. Okay, we will see the alternative. It is having double bond O. This is high electronegative than this. Therefore, this will shift the pi bond this side. So it will act as electron withdrawing group. Therefore, because of this oxygen, carbon is getting electron deficiency. Therefore, it will pull the electron cloud from phenyl. Therefore, it is showing minus R effect. So minus R group means the atom which is directly attached to phenyl ring will have multiple bond with high electronegative atom. This high electronegative atom will pull the pi bond. Therefore, here electron deficiency is created. Therefore, it is pulling electron cloud from phenyl ring. Therefore, it is showing minus R effect, so that it is deactivating the phenyl ring, and it is directing electrophile to attack at meta position. Okay, so it is electron withdrawing group, it is electron donating group. Suppose like this is there, alkyl group is there. Alkyl group is there means it will act in what way? Here what happened means hyperconjugation possible. This bond is shifting like this. This bond is shifting like this. Hyperconjugation is possible. In the hyperconjugation, this group is electron donating group. Therefore, it is activating the phenyl ring towards electrophilic substitution. It is making the phenyl ring. It is directing the electrophile to attack ortho and para positions. Therefore, it is ortho para director. Now, halogens will take, particularly halogens. We are taking halogens, and these halogens will take. Okay, mainly halogens. We are discussing separately about halogens. It is having lone pair. This atom is directly attached to phenyl ring. It is having lone pair. Therefore, it shows plus R effect. So plus R effect, it shows plus R effect in the sense it is ortho para director for electrophile. It will direct the electrophile to attack at ortho and para positions of phenyl ring. But it shows minus I effect. Due to minus I effect, it is deactivating the phenyl ring. Okay, so remember that in the halogens, it will show plus R effect. Therefore, it is ortho para director. It is showing minus I effect. Due to minus I effect, it is deactivating the phenyl ring. Remember that. Now we will go for this phenol. This oxygen shows plus R effect and also minus I effect, because oxygen is more electronegative than carbon. So it is showing minus I effect. Even then, plus R is dominating, minus I is not dominating. But in halogens, only separate case. Okay, so halogens are deactivating the phenyl ring, but ortho para director. Okay, but the rest of the cases activating the phenyl ring and direct and ortho para director. It is electron withdrawing group, it is deactivating the phenyl ring, and it is meta director. Okay, so in this way we have to find. So now we will take anisole. In the anisole, oxygen is directly attached to phenyl ring. Oxygen is having lone pair, therefore it shows plus R effect and also minus I effect, but plus R effect is dominating, therefore it is activating the phenyl ring towards electrophilic substitution. It is ortho para director. Okay, therefore in the anisole, how the electrophilic substitution reaction takes place, that we got an idea. Now we will take the anisole. We are taking anisole. This anisole we will take for nitration. Nitration in the sense, what is a nitrating agent in the sense corn nitric acid plus corn sulfuric acid. Corn nitric acid plus corn sulfuric acid is the nitrating agent. So here what is the electrophile in the sense, NO2 plus is the electrophile. NO2 plus is attacking at ortho position, otherwise para position. Okay, therefore at ortho position NO2 group goes, and at para position NO2 group goes. Okay, NO2 group goes. Okay, ortho nitro anisole, para nitro anisole, we got it. Okay, next we will take to this what we will add in the sense bromine and acetic acid. Bromine in acetic acid we have taken. Then absence of FeBr3. FeBr3 is not there. FeBr3 is not there. What happens means bromination takes place. At ortho position, bromination takes place. At ortho position, bromination is taking place, and at para position, bromination is taking place. Okay, this para product is major, ortho product is minor. Okay, generally ortho is minor. Generally ortho is minor, para is major. Okay, sir. Then Friedel-Crafts alkylation we'll see. Friedel-Crafts alkylation. Okay, then next we are seeing Friedel-Crafts alkylation. Now we will take a alkyl halide. We will take. We are taking alkyl halide. Here we are taking a anhydrous AlCl3, anhydrous aluminum chloride, carbon disulfide. We will take alkyl halide. We are taking anhydrous aluminum chloride. We are taking carbon disulfide. We are taking. Okay. What happens means alkylation is possible. Alkylation is possible at ortho position, and alkylation is possible at para position. Alkylation is possible at para position, we can say. Okay. Sir, here this is called Friedel-Crafts alkylation, we can say. How Friedel-Crafts alkylation is possible? What is the electrophile here? That we'll see. Now we are taking aluminum chloride. We are taking aluminum chloride. To this, what we are adding in the sense of methyl chloride, we are adding methyl chloride. We will write like this. Methyl chloride. Here what happens means chlorine is having lone pairs. This is attacking here. This bond is shifting. Therefore, what we are getting in the sense CH3 plus is the electrophile here. Here what is the electrophile means CH3 plus is the electrophile. Okay. CH3 plus is the electrophile in this Friedel-Crafts alkylation. Next, Friedel-Crafts acylation we'll see. Friedel-Crafts acylation. Here we will take acylating agent. Acyl chloride we have taken as acylating agent. Then we will take a anhydrous AlCl3. Here, how the electrophile is generated, that we will see. Now we will take anhydrous aluminum chloride. Anhydrous means no water. This acetyl chloride we will take. This acetyl chloride is like this is there. Acetyl chloride we have written like this. It is going like this. This bond is shifting like this. Therefore, what is the electrophile created in the sense so and so electrophile is created? It is called acylium ion. Acylium ion. This acylium ion, this electrophile is attacking the phenyl ring at ortho and para positions. Therefore, we will get at ortho position acetyl group we will get. Then at para position acetyl group. Then at para position acetyl group. Okay. This is Friedel-Crafts acylation, we can say. Next, we will see Friese rearrangement reaction. Next, we will see Friese rearrangement. Next, we will see Friese rearrangement reaction. We'll see. Okay. Friese rearrangement reaction. Now, Friese rearrangement reaction in the sense what we are taking in the sense phenolic ether we are taking. We are taking phenolic ester we are taking. We are taking phenolic ester. Phenolic ester. The phenolic ester is what in the phenolic ester is it is called phenolic ester. It is called phenolic ester. This phenolic ester is taken and aluminum chloride is added, then it is heated. Okay. Now what happens means so and so is produced. Here COR, then OH, here COR. Okay. This is called a Friese rearrangement, we can say. This is called orthoacyl phenol. Orthoacyl phenol. It is para-acyl phenol. Okay. Now, when the temperature is low, less than 100 degrees Celsius, para dominates. When the temperature is high, greater than 100 degrees Celsius, ortho dominates. Ortho product dominates. Okay. So what is the mechanism involved here? That we'll see. Now, we are taking phenolic ester. We have taken a phenolic ester. We are taking aluminum chloride. Aluminum chloride. This oxygen is having lone pairs. Now, this is contributing to this one. This bond is shifting. Therefore, what is produced in the sense RCO plus acylium ion is produced. Okay. This is converting into what in the sense O AlCl3, here phenol, here phenyl group, okay. Phenyl group is there. Next what happens means this acylium ion attacks at ortho position, or attacks at para position. Okay. So it is attacking at the ortho position, otherwise para position. It is coming here. This bond is shifting here. So that we will get here AlCl3 will be there. Here phenyl ring. Here pi bonds will give. Here positive charge. Okay. It is going for resonance. So next step, what happens means this bond is shifting here. This bond is shifting here. Then this bond is shifting here. Here we have to write minus. I left it. That minus we have to write. This bond is shifting here. This bond is shifting here. This O becomes O minus. It is becoming H plus. H plus combining with O minus and becomes OH. This AlCl3 leaving. Therefore, we got so and so product. So and so product we got. Okay. It is called a Friese rearrangement, we can say. So phenolic ester undergoes Friese rearrangement to give ortho-acyl phenol and para-acyl phenol. At low temperature, para is dominating. At high temperature, ortho is dominating. Why we have to give high temperature to ortho? In order to avoid steric hindrance. That's all. So at low temperature, para is dominating, we are saying. Okay. So this is called a Friese rearrangement, we will say. So next, we will go for epoxides. Epoxides, another name is called oxidants. So next we are going for epoxides. We are going for what in the sense epoxides. This epoxides, another name is called oxidants. Epoxide, another name is called what in the sense oxidants, we can say. Okay. Now for this case, we will take alkene. We are taking alkene. To this alkene, we are adding a peroxy acid. Peroxy acid we are adding. What we are getting in the sense epoxide we are getting. So what is peroxy acid? That we will see. Peroxy acid in the sense we will take what in the sense benzoic acid we will take. We are taking benzoic acid. This benzoic acid we will convert into peroxy acid. How? That we will see. This is called peroxybenzoic acid. This we can call it as peroxybenzoic acid. Okay. Next, we will take acetic acid. We will take acetic acid. This acetic acid we will convert into peroxyacetic acid. How you see that? It is called peroxyacetic acid. Okay. Next, we will take that metachlorobenzoic acid. We will take metachlorobenzoic acid. This is called what in the sense metachlorobenzoic acid. Here we will keep a peroxy linkage. We will keep. This is called a metachloroperbenzoic acid. Metachloroperbenzoic acid. These are called peroxy acids. Why they are called oxy acids? Because OH group is responsible for acidic nature. OH group is giving H plus. Therefore, these are called peroxy acids. So now we will take alkene. We are taking alkene. To this alkene, let us add peroxy acid. Let us add peroxy acid. What we are getting in the sense epoxide we are getting. This epoxide name is what? Epoxide means cyclic ether. Cyclic ether is called epoxide. Okay. This epoxide name, what is the name of this epoxide? That we will see. Okay. Now here it is first carbon, it is second carbon, it is third carbon. 3 carbon atoms are there, therefore propane. 3 carbon atoms, therefore propane. Then this oxygen is called epoxy. This oxygen is called epoxy. It is present between 1 and 2 carbons. 1 and 2 carbons. Therefore, we can call this is as 1,2-epoxy propane. We can call this is as a 1,2-epoxy propane. We can call. So, what is the mechanism involved here? That we will see. Now, this epoxide will take. Sorry, this peroxy acid will take. This peroxy acid we are taking. This peroxy acid, then we will take this alkene. This alkene we have taken. Okay. Now we will see the chemical reaction. We will see how the chemical reaction is possible. That we will see. This bond is migrating. This bond is migrating. This bond is migrating, then this bond is migrating like this, this bond is migrating like this. Okay, that means what happens, you see that. So this oxygen hydrogen bond is migrating towards which side, in the sense migrating towards this carbon side. Now see that this bond is making shifting to this bond is shifting to this. Okay, this oxygen takes this bond and makes a bond with this carbon. This pi bond is shifting, this pi bond is forming with this oxygen. This bond is completely shifting as here, therefore it becomes a double bond. This pi bond is shifting to oxygen, therefore it becomes O minus. This hydrogen loses this bond so that it becomes H plus. This H plus is combining with this oxygen. Okay, therefore what happens, you see that this R we will write this single bond C, single bond C, this single bond becomes a double bond, this double bond becomes single bond O, this O is making bond with H, it is carboxylic acid. Okay, next we will see here this CH2 will write, that CH2 we are written, this double bond we will write it as single bond, this we will write it as CH, this we will write it as methyl. Okay, now see this oxygen takes this bond and making bond with carbon. Okay, making bond with carbon, while this pi bond is shifted towards with this oxygen, with this oxygen. This is called epoxide. Okay, epoxide or oxidane, it is called cyclic ether. Okay, so for getting cyclic ether we are treating alkene with peroxy acid. So alkene on treating with the peroxy acid, what we are getting, in the sense epoxide we are getting, sir. Now we will take a, now we will take this is butene, this butene we will take. It is a 1 2 3 4 carbon atoms are there, therefore but and a double bond present at second carbon. Okay, it is cis because similar groups are on same side, therefore it is cis. Now this is treated with what, in the sense RCO3H, peroxy acid. It is treated with peroxy acid. So what we are getting, that we will see what we are getting, in the sense now here see this oxygen is adding in between these two carbons, these two carbons making bond with the oxygen, that is a product, no. So therefore carbon 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 double bond becomes single bond, and these two carbons making bond with the oxygen and making cyclic ether. Okay, now here one methyl group we will give, here one methyl group we will give. Okay, so for both carbons we have given methyl groups. Now this carbon is having one hydrogen, this carbon is having one hydrogen. Where those hydrogens will be present, where those hydrogens will be present, that we want to know it. If we consider these two carbons and this oxygen is in a plane of this screen, then we can say these two methyl groups are above the screen in the sense projecting towards us. Then these two hydrogens is rear of this screen, rear of this screen. Why should we say like this? Because see the mechanism. In the mechanism, if you see, this oxygen is making the bond with this carbon, while this pi bond is formed with this oxygen. Both process should take place simultaneously. Both process should take place simultaneously, in the sense this carbon, this oxygen should be in a plane. Okay, that means this oxygen is adding to both carbons at a time, this oxygen adding to these two carbons at a time, that means syn addition. Okay, syn addition in the sense so what will happen, in the sense syn addition in the sense, when this oxygen is attacking this double bonded carbon from up, suppose, then all the four groups will go down. Okay, now first we will take this alkene will take. In this alkene, these two hydrogens, this carbon, this hydrogen and carbon, all are in one plane. Okay, Now this oxygen is attacking these two double bonded carbons from up, in the sense these two hydrogens, this hydrogen, this carbon will go down. Okay, because it is a syn addition. Therefore, we will say like this. Okay. So syn addition. Therefore, these two hydrogens down we have written. Okay. So what isomer will get means a cis compound on syn addition will give cis compound. Okay, it is cis 2, 3, 2, 3 butene oxide. Butene oxide we are saying. Why 2, 3 in the sense it is first carbon, it is second carbon, it is third carbon, it is fourth carbon. At second and third carbon, oxygen is there. Therefore, oxide present at 2 and 3 carbons. Butene 2, 3 oxide. Like this we can say. Why it is cis in the sense similar groups are on same side. Hydrogen, hydrogen are on same side. Therefore, cis. So now we will take trans. We will take here methyl, carbon, hydrogen, double bond carbon, hydrogen, methyl. It is a trans butene. It is a trans isomer. It is trans isomer. Now we will treat this with peroxy acid. Peroxy acid. What we will get? That we will see C single bond C here with O like this is there. Now one methyl group is projecting towards us, in the sense one methyl group will be down, will be rear. Then this hydrogen is projecting towards us, means this hydrogen is rear. Like this ether will get. Therefore, it is also trans. Why it is trans means hydrogen, hydrogen similar groups, they are on opposite side. Therefore, trans. What is the name of this one in the sense 2, 3 butene oxide. 2, 3 butene oxide. That means this is first carbon, it is second carbon, third carbon, fourth carbon. Oxygen is attached between second and third carbons. Therefore, trans 2, 3 butene oxide we can say. Sorry. Next reaction we'll see. Alkene will take, that we will treat with chlorine water. We will get a chlorohydrin. Chlorohydrin we are taking. This is treated with aqueous sodium hydroxide solution. We are getting what in the sense epoxide. We are getting epoxide. We are getting okay. So alkene is treated with chlorine water. We are giving chlorohydrin. Chlorohydrin on treating with aqueous sodium hydroxide. We are giving epoxide. We are getting okay. So now what is the mechanism that we will see? Now chlorine water will take. Chlorine water. Chlorine water we have taken like this. Okay, chlorine water we have taken like this. This chlorine is having chlorine atom is having 3 lone pairs here. Now alkene we will take. We are taking alkene. So this pi bond is attacking this chlorine. This bond is shifting. Therefore, what we are getting in the sense so Cl minus is leaving. Okay, Cl minus is leaving. Okay, here what had happened? Here this chlorine is having 3 lone pairs. This pi bond is attacking this chlorine. This sigma bond shift completely towards this chlorine. Therefore, this chlorine leaves as Cl minus. Okay. Now, since the Cl is leaving one electron, therefore positive charge is there. Okay. This is called cyclic carbonium ion. Cyclic carbonium ion is produced. Okay. Then Cl minus can attack, otherwise water can attack. Okay. Nucleophile will attack now. How the nucleophile is attacking C? Therefore, we will get MECH. Here what is there? Means Cl is there. Here CH2. Here OH is there. From here H plus we will remove OH. Therefore, it is called chlorohydrin. Chlorohydrin means one chlorine will be there, one OH group will be there. One alcoholic group and